Thank you, thank you, thank you. Welcome back. It's been a little while. Today we're going to talk about boilers for energy risk engineers. This is something that is outside of my main field, but I've been in a lot of boilers and I've been to a lot of boiler failures and inspected a lot of boilers. So hopefully I can share some experience and some stories with you. And I'm going to change it up a little bit. Normally I save all the best for the last, and I realize that most of you viewers don't watch past the first or second commercials. So I'm going to front load it and put all the best stuff up front. I'm going to give you all the experiences, not all, I'm going to give you several experiences that I've had with boilers to make it worth watching the rest of the video to figure out how to prevent these kind of things from happening. With that, let's get into it. So what happened? This was about a 700 megawatt boiler. We had a master fuel trip failure. What does that mean? Well, basically these big, huge power boilers are set up to trip the fuel going into the boiler if other things go wrong. It's just a safety net to make sure that we don't do what we actually had happen here. And what happened was the master fuel trip relay did trip the plant, but not all parts of the plant. So the fuel continued to be fed to the boiler while the feed water was shut off. So that part tripped, but the fuel part didn't. So we ended up dry firing the boiler, and the inside of this huge boiler looked like spaghetti tubes. Back in the 90s, it was about a $3 or $4 million loss. Today, it would be probably 10 times that. We had a pneumatic control line for a vent damper fail. Now, what happened here was this was a package boiler, something you'd see in a chemical plant or a power plant just to warm the equipment or warm the process. And they were trying to start the boiler. It was a cold day, very, very cold day. And they had a failure to start. So, you know, the start cycle is to run a purge, especially after a failure to start when you've already dumped fuel in there. You know you want to purge that fuel out before you put another fresh batch of fuel and air in, because that first batch didn't ignite. You've got an unknown concentration of fuel and air. Get it out of there, get a fresh batch in, and do it right. Well, they tried that 3 times, not realizing on the 3rd time the boiler exploded, trapping one of the operators in that boiler room. The other operator was outside. He used a crowbar to break open the door and get in and rescue his buddy. But during the investigation of what happened, we found that the air supply line to the ventilation damper had moisture in it, and that moisture froze. And even though we were doing the purge cycle, no air was getting out of that ventilation damper. None of that fuel air mixture was actually being purged out. So that was a lesson learned, that when you have pneumatic systems, you have to maintain them, and especially when it gets cold outside. All right, another one we had. This was on probably one of the very last few coal power plants built in the United States. And during the commissioning, I watched all kinds of mistakes. But one of them was that they actually hydro-tested the boiler with pond water. I mean, rocks, sticks, mud, everything was just pumped out of the pond into the boiler by this contractor. And after they did that, they sampled the water to see how much chloride was in it, and they found out they had totally exceeded the manufacturer's recommendations for chloride limits. And they started to have intergranular stress corrosion cracking, and they had tube leaks for the whole first year. We weren't involved with the project after that. I imagine they still have problems because there's dead legs in boilers that you can't flush the water out of, so it's just going to take years for those chlorides to get out. Another problem we had, level switch failure due to mineralization. This was in a chemical manufacturing plant, and like I said, the water that boils in there leaves the minerals behind, and the water steam pure goes out, but those minerals just concentrate. And if you don't blow down the boiler periodically, you're going to crap it up on the inside. And what happened was this level switch thought that there was plenty of level in there because it was crusted over and stuck, and it didn't drop when the water level went down. The water level went all the way down and dry fired the boiler. Okay, this is very bad to dry fire a boiler. You pretty much ruin them. And then finally, we had a coal plant that was converted to burning pistachio hulls. Basically, anytime you take an old coal power plant and try to convert it to burn other stuff, what you're doing is taking something that was designed to burn one element in the periodic table, carbon, and you're now asking it to burn all the elements in the periodic table, because municipal solid waste fuel, you have no idea what's in that garbage. There's just all kinds of things that are going to be combusted. And don't forget that we're going to have high temperatures. So you add high temperatures to unknown chemical reactions and you're going to get some crazy corrosion going on. And that's what we had here. In addition to the corrosion, the pistachio hulls themselves were very abrasive, right? So even after they were burned, they were erosive. So a lot of the design that was based on just moving the hulls and moving the fuel forgot the back of the process and forgot that it was going to erode it. And they tried to do some fixes that never ended up working, turned into a $50 million insurance claim, believe it or not. All right. Now, what I'm going to talk to you about today is not code compliance. I'm not about code compliance. If you want to find code compliance, search for it. I'm here to talk to you about risk management and basically how to apply lessons from life to situations you might find in the future and just give you a taste of what boiler risk engineering is all about, okay? So we've already talked about examples of boiler losses. Hopefully we still have you here. And we're going to continue to talk about boilers, you know, what they're used for in chemical and power plants. We'll talk about what different kind of boilers there are. We'll talk about mechanisms of damage, how boilers do get damaged. We'll talk about the property risks, not so much life safety risks. There are some out there. And we'll talk about managing the risks. So let's get into it. Chemical industry mainly uses boilers for process heating and for energy supply for the process. And these are going to be smaller package type process boilers. Now, some big chemical plants use some of their own process to boil water. And we'll talk later about heat recovery steam generators. Power plants, okay? Power plants, they need steam to turn their turbines, so they're going to make electricity. This is their bread and butter. It's the main purpose for boilers in power plants is to make steam to make electricity. However, when a power plant's cold and shut down and the boiler's not operating, we need smaller package boilers to warm things up to get started so that that big heavy turbine that's going to have steam rolling through it can't just be turned on and cranked up at full speed. It has to be slowly warmed up so that everything expands nice and gradually and doesn't cause rubs that could cause failures. All right, so what kind of boilers are there? There's fire tube boilers, and these are used, again, in smaller applications. This is what we would see. The fire is occurring in a firebox. The flames are going through the tubes. The water is on the outside of the tubes being contained by the shell, so the water and steam are outside of the tubes. And in a water tube boiler, the water is inside the tubes. And this is what you're going to see in a big power plant. You're going to see large industrial processes using this where they actually put tubes of water going through the firebox. And that's how the water boils in the tubes. So what can go wrong with boilers and what are the property risks? Well, we can have it. Yeah. So how do we stop the explosions? Let's look for double block and bleed valves. Okay, in the old days when they just thought they isolated the fuel supply, they learned that sometimes that isolation valve can leak. And that if you think the boiler's shut down, but you've got a slow leak occurring, that we've had some very catastrophic failures due to that. So the philosophy has been to put in two isolation valves, two block valves. Well, how do you know if the first one's leaking? You put in a bleed valve. You put in another pipe in between these two valves, and so you have a valve on that pipe. And when you isolate the fuel supply, you close both of the isolation valves and you open the bleed valve so that if any fuel gets past the first valve, it's going to go out the bleed line and not push up against the next valve, which could be leaking too. So this is how we've managed to reduce the frequency of explosions in the industry over the last few decades. Double block and bleed. Follow the codes to get it right. Okay, ventilation systems. We talked about the purge. We talked about the problems with purging, that just pushing the button doesn't mean that the air actually moves. We have to really learn that lesson that, you know, you've got to have some confirmation that the ventilation dampers have opened, a limit switch that tells you that they're open, a flow switch that tells you that air is flowing. There's lots of things that you could do to verify the purge, but just pushing the button and seeing the light come on is not enough. What else do we do to prevent explosions? Flame safety scanners, okay, they're important because there's a potential for flames to go out. Your burner flame could go out. And in the environment of fossil fuel burning in a boiler, we create soot. That soot can get on the flame scanners and make them unreliable. Sometimes they can miss what's going on. A lot of times we get false trips because they think that the flame is out when really they're just covered with soot. Low NOx burners. Low NOx burners can, they are being brought in to industry to improve environmental conditions. But what can happen is that a low NOx burner achieves its low NOx status by burning a colder flame. NOx is created by very high temperature combustion in the presence of nitrogen, which is air is 80% nitrogen. So if you're burning air, you're making NOx, and the higher the temperature flame, the more NOx you're making. So if you can have a colder flame, you can make less NOx. The problem with a colder flame is that it's a flicker. It's about to go out. It's ready to extinguish itself. So when you have a flame scanner trying to watch a flickering flame that tries to go out, that flame scanner is going to have a lot of trouble. So you need to have a special flame scanner for low NOx burners. So let's get on board, get the right kind of flame safety scanners. Let me say that when they don't work, when they're giving you false trips, the operators will turn them off, and you'll get all kinds of issues when they don't have any flame safety scanners at all, like potential explosions and puffs. Now let's move on into mechanical integrity. You talked about fire and explosion. There's just about so much you can do. It's not really the kind of thing that suppression systems are really going to help. You can have burner front fire protection systems on oil burning boilers, which there are probably not too many of these days anymore. It's very expensive to burn oil to make electricity. So let's talk about mechanical integrity. What can go wrong? Waterside corrosion. Well, waterside corrosion is when you get things going on in your process that causes a chemical reaction. You get thinning of the tubes and pitting and stress corrosion cracking. Fireside corrosion, this is where in the firebox, and we talked a little bit about burning pistachio hulls and burning garbage, how we can develop corrosion products that are not typical in just burning hydrocarbons. Okay, another thing that we can have is overheating. If we get a spot where we don't have adequate flow of our water and steam, we're going to overheat it. Remember, we're trying to boil water and steam, but the water and steam are coolants for this firebox. And if we don't have the coolant, or we don't have enough going through a certain area, we'll get overheating and potentially failure. I saw this, happen when a rag was left in the feed water line, and it went up and got into a feed water heater, and it just blocked it until the tubes failed. Just blocked a few of the tubes, so it's hard to detect small blockages in these things. Stress rupture. Prolonged exposure to high stress levels can cause rupture in boiler tubes. Erosion. Again, we talked a little bit about the erosion of the pistachio burner, but again, even water and steam can erode, like feed water heater lines, that kind of thing. I was at a power plant and this was 2 units, 850 megawatt nukes. They were pressurized water reactors, so the steam was not radioactive, but we blew out a feed water heater elbow, and it filled the entire turbine deck with steam in seconds. I mean, less than a minute. And of course, everybody came running out of their offices to go see what the noise was about. And after the emergency, management told us, don't run to the noise. Please run away from the noise. So that was a lesson learned on noises in big plants. All right, the fatigue. Loading these things up, if you have to heat them up, cool them down, heat them up, cool them down. If there's a lot of cyclic service, you're going to see fatigue. Agglomeration. If you're burning solid fuel, you can get solid particles that can obstruct the flow paths. And again, any kind of obstruction of flow can result in overheating. It's like slagging and fouling. This is after the fuel's burned. And just the efficiency, just having the extra layer of insulation on the tube will have a possibility. Now, this has happened and it causes stack collapse, where you have the gases that leave the boiler go up into the stack, and if you're not effectively removing some of these ashes and slag, it'll plate out on the or it'll deposit out on the stack, the inside of the chimney, And there was a issue where some guys were in a chimney like that cleaning those out, and they were basically chiseling it away, and they had a chunk break out, and when it broke off the inside of the chimney, it went down to the bottom, but it was the size of a Volkswagen, and as this big chunk fell down, it compressed the air on its way down in the bottom of this chimney. And when it finally had enough pressure, it blew out the bottom of this chimney, and the stack collapsed. It fell over with those gentlemen in it. 3 people died. Anyway, slag accumulation. Caustic embrittlement. Concentrated alkaline solutions can weaken the boiler materials. High temperature corrosion. We talked about what goes on when you add high temperature and then doubtful water chemistry or doubtful fuel chemistry. Issues with heat recovery steam generators, flow accelerated corrosion, chemistry challenges, air in leakage. Okay, these are typical for HRSGs. Now, how do we manage and how do we mitigate the risk? Well, regular maintenance is important. We have to do inspections, cleaning, repairs, proper water chemistry. Again, this comes up if you inspect it, maintain it, clean it, and operate it properly, you're going to have a good result. So the thing, operator training, you have to teach proper startup and shutdown and emergency procedures. We had operators that were so frustrated with flame safety scanners, they turned them off, and when they lit their multi-level boiler, they would light off one row of burners or one deck level of burners, and then on the next level, they would just start blowing coal in, let the coal drift down to that level, catch on fire and puff, to get this level burning, and then they would do that the same way all the way up. So they were having mini boiler explosions, causing fatigue, causing stress all the time because they were frustrated with the false trips caused by the flame safety scanners. They have to be taught that they need to turn in those false trips, explain them to management and engineering. Don't just take your own precaution and override it. Okay, it's very, very important that problems are identified and raised to the top. Safety controls, pressure relief valves, temperature sensors, flame monitors. Make sure the flame safety scanners are right for the technology of burners that you have. Level controls, fuel controls, these are all safeties to prevent explosions and fires. Okay, what can go wrong? What can happen in process boilers? We got to keep an eye on some of these things. I'll go quickly through them. I don't want to read them all to you, but deaerator cracking we want to look at in process boilers. Feedwater line erosion is something that we need to look at. Water side failure mechanisms. Okay, power boilers, a little bit different than process boilers. These are going to be the huge, big power steam generation boilers. We want to look for water side failures, fire side failures, ash fouling, slagging. I never forget the first time I went on a risk engineering visit that was a combined visit with fire protection engineers and boiler machinery engineers. The fire protection engineers could only offer suggestions and advice to install fire protection or to do things that were going to cost money but not have a direct impact on revenue immediately. Whereas the boiler machinery engineer noticed a problem with fouling and noticed that they had problems with their soot blowers and shared with them a lesson that he'd learned from another facility that would make their soot blowers more reliable and easier to use and just more likely to be online when they needed it. So they were excited. They wanted to hear more about it. They wanted more information. They were writing down numbers and phone numbers. And it was obvious that the boiler machinery part of risk engineering has something to offer that the facilities want to hear. The fire protection side, unfortunately, you're giving them bad medicine, so it's going to be a little bit tougher. But this was really good news to know that there's some advice that people want, and it's this boiler machinery stuff. General failure mechanisms that can happen to process boilers: creep, fatigue, stress, corrosion, cracking. Again, inspections, monitoring, maintenance are all vital. With that, thanks for watching. Hope I didn't leave too much out for you. I know it's a big topic, and if you want more about boilers or energy risk engineering, let me know in the comments. Love to keep doing this. Thanks again.